Good morning, everybody. Welcome to episode 3 of AlgorithmsThread. In this episode, we'll be talking about segment trees. A couple things I should mention before we begin. First, this is going to be a little bit easier of an episode. It'll cover a little bit more common topic that a lot of people already know. So if you're already really familiar with segment trees and you know all this, feel free to just skip this episode. The reason that I'm doing it is because the next two episodes will be about very difficult segment tree things that most people don't know, and I want this episode to be here for people to go look back on in case they're not familiar with it, because I don't want to spend time in those talking about what a segment tree is for people who aren't familiar. They can just go watch this video instead. The second thing is that Matt Fontaine, who's the person who made Algorithms Live, already had a video on segment trees. For him, that was episode 4 of his series, and it's a very good episode, so if something in this you find lacking, definitely go and watch that. The one criticism that people may have is it's a little bit long, so this should be hopefully a little bit more condensed. And the other thing is, in this video I'll talk about object-based segment trees, which is how I write them, and I think those are a little bit easier than array-based. But if you're more comfortable with array-based, then feel free to look at how he does it as well. Alright, so what are segment trees and why are they helpful? The first thing that you might want to do with a segment tree is say you're given some array, and you need to do something with that array. Maybe you need to update the array and then answer questions about the array, or maybe you have to do something else. So you've got like some continuous block in the array, and it's possible that you have to update maybe some position. So maybe you have to do updates. And then you also want to do some sort of, you want some information about the array. So maybe you want like range sums, or maybe you want range minimums or range GCDs. So you want some sort of query that you have to answer. And the great part about a segment tree is that they can do both of these things in log n time. So if n is like 10 to the 5th, they can do both of these in about like roughly 20 operations. So a very small number of operations compared to like the size of the array. So let's look at some examples. So maybe you have some array, and your array looks like 3, 1, 4, 7, 6, 2, 2, 4, 3. Let's get rid of this one here. That way our length is the power of 2. So what we can do is we can take this array and we can split it into 2 separate groups. So the first thing we're going to do is we're going to have the entire array in one group, and then we're going to have just the first half of the array in the first group and just the second half in the second group. So this will be 3, 4, 7, 6. This will be 2, 2, 4, 3. Then we'll split it up in half again. So 3, 4, and then just the 7 and the 6 here. And then we'll have 2 2s here, and then a 4 and a 3. And then we'll split everything up into just it by itself. So if you've ever learned about merge sort, maybe in school in AP Computer Science, something like that, you'll notice that this is exactly how merge sort works. So when you sort some array, you split it up into 2 halves, you sort both of the halves, and then you combine them in linear time. And that winds up having an n log n runtime. Similarly, this is also n log n. So why is it n log n? Well, you have log n different heights, because each height, the size of each group will double. And you can only double a logarithmic number of times until you pass some number. So this right here will be roughly log n. And then the number of nodes in each layer is no more than order n. So there are at most order n things in each layer. And in this case, the way I've drawn it, it would be order n. But in reality, usually this node right here doesn't need to store all of these things. Usually the node can only store like a constant amount of information. Maybe the sum across the range, maybe the minimum, something like that. And in that case, then it only uses order n memory. And the reason for that is because you've got 1 node here, you've got 2 nodes here, 4 nodes here, 8 nodes here. The total of all of these numbers isn't really 8 times the height. It's more 8 times 2. And 8 times 2 it's about as big as 8. So if 8 gets huge, if it's some huge number, it's like that number times 2, not that number times the log of that number. So that's why segment trees have a roughly linear amount of memory. All right, so I've described this structure here. How do we go about using it and doing stuff with it? So maybe one thing that you want to do with this is maybe you want to answer some queries. And each query, we'll use the example that Matt used in his video. Each query is like the range minimum, for instance. So maybe you want to find the minimum of these or let's do the minimum of these three numbers here. So what you can do is you can find the minimum of these numbers in logarithmic time, like I mentioned earlier. So how do you do that? Well, there are three different cases that you can look at in a particular node. The first case is the range is entirely disjoint. What does disjoint mean? That's like a really fancy word. So if this is the range you're responsible for, like this is you, and the other range that you're looking at that someone's asking about, maybe it's this range here. So they're entirely separate. That's the first case. The second case is the query range covers you. So what does that look like? Well, again, you've got your range here. Maybe that's you. And this one, I guess, has a bit more clear meaning. So that would be it covering you. And then there's this third case, which is they intersect, but it doesn't covers you. So it's like, well, I guess it's like everything else, right? So this can happen in two different ways, I guess. One way might be it's like some smaller thing inside of you, like that. And another way might be it like starts outside of you and it like crosses you. So it intersects you, but it doesn't cover you. So these are the three different cases. And what we can do is we can look at this query range here. I guess it might be helpful to draw this in blue, that way it matches the other picture. So we've got this blue query range here. And what we do is if it's entirely disjoint, then we just return negative infinity, right? Because we're trying to get the max on some range. So negative infinity won't matter. So in this case, we just like return negative infinity. If it covers you entirely, then the minimum in that range of the things you're responsible for is going to be the minimum of all the things you're responsible for. So in this case, we just return our minimum. In all other cases, we're not really sure what the answer is. So this is like an example of case 3 here. This is case 3. And in case 3, we're not sure what the answer is. So what we have to do is we have to go to both of our children, have both of our children answer that question. So that's what we're going to do here. We're going to go to both of our children, and we're going to say, all right, both of these children have to answer the query of this range. And then after we have the answer for both children, we'll take the min of those two answers, and that'll be the final answer. Okay, so how would each child do this? So again, in this left child, we're at case 3 again. So it doesn't entirely cover us, and it also isn't entirely separate for us. So what we're going to do is we're going to go to both of the two children here and ask each of them to solve it for us. So now we're trying to solve this range here. And in this left child, this 3, 4, we'll notice that in this case we're at case 2. So it's entirely, or sorry, we're not at case 2, we're at case 1. It's entirely disjoint. So in this case, we can just return negative infinity because it's entirely separate from us. So we know the minimum in the blue range is not going to be the minimum in the 3, 4 node. So here we can return like negative infinity, or the maximum, sorry, the maximum won't be the maximum here. All right, cool. Now we're in this node, and again, it kind of covers us, so we have to go down again. And what you'll notice is, as you go down, you only wind up working your way down to 2 different leaves. So the first leaf you work down here, I guess I'll circle it in green. This is the first leaf we're going to work down to. And the second leaf you work down to is going to be this leaf here. So the first and last part in that range are going to be the 2 leaves that you might hit. You're not going to hit any other leaves in the tree. And in fact, you'll break as soon as you get the chance of whether you're inside or outside. So that's why the runtime is roughly logarithmic. That's not really too formal of a proof, but you'll notice for anything in this size, if there's a really big, you can imagine if there's a really big range here, that's going to be covered by this blue range. And similarly, if there's a really big range outside, we'll skip all of that because it's entirely separate from this blue range. So that's where the log n comes from. Because they're log n heights, and we go down the tree like at most twice. Okay, so yeah, let's continue what we were doing here. So we've got this 7 and this 6. The 7, again, is entirely disjoint from the blue range. So this is going to be case 1. And we can return our negative infinity here. But the 6 will be, it's not entirely disjoint. So the 6 will return the value 6. So we'll draw that in blue. So it returns the 6. So now the answer for this node is going to be 6 for the same reason. So this will return the 6. And now this node here will also return the 6 because it looked at its two children, found the bigger of those, which was the 6, and it can return that. All right, now the same thing happens in the right child, except in this case, we'll stop at this node right here. And we can stop at this node because we see the blue entirely covers it. So since the blue range entirely covers it, then we can return early. And we'll see that this this just returns 2. Because the maximum in this range is going to be 2. So this range returns 2. This range here, it went to its left kid, like we mentioned, but this is going to be, so this is case 2 here. It also returns 2. And then this right here is it's case 1. It's entirely disjoint. So this will return negative infinity. All right, now we're at this node right here, and this node will return, it'll return 2, because 2 is the bigger of 2 and negative infinity. And now finally we're in this top node, and this top node looks at the 6 and the 2, and it returns the 6. So this was a bit of a complicated way of finding the min of 3 elements, but if instead of just 3 elements we had like 1,000,000 elements and we had to look at 100,000 of them somewhere in the middle, this would be a very fast way of doing it. We could look at comparatively very few nodes, because most of the nodes would be just giant chunks, and we can either say, all right, this entire chunk doesn't matter, or this entire chunk is inside the range, so we just need to look at the minimum of this entire chunk, which we've already calculated. All right, so I've already done a video on RMQs, and if this is the only thing that you wanted to do, you could use an RMQ for this, and you could do a very similar thing. So you might wonder, well, why is this useful? And the main reason is because it's very fast in order to update segment trees, and you can't update RMQs at all. So if you're doing like a sparse table or an RMQ and you need to update things, you have to just rebuild the entire thing from scratch. But if you're doing a segment tree, it's very easy to do updates. So I'm going to erase this picture because it's pretty big, but I'll keep these 3 cases at the bottom because they're kind of helpful. So we've got some ranges. So here's our big range. It splits into 2 halves. Then each of these split into 2 halves again. And then each of these split into 2 halves at the very bottom. So there are 2 types of updates you can do. You can do point updates and you can do range updates. And I'll talk about how you can do both of them. So let's do point updates first because they're easier. If you want to update some particular point, maybe you want to update this node here, you're going to have to update that node, and you're also going to have to recalculate the answer for any node that is a parent of that node. So this green node you'll have to calculate the answer for. Also, this node here you'll need to recalculate the answer for, because its min might change when you change this bottom node. And similarly, since this min might change, you also have to update the new minimum for this node and for this node. And it's pretty clear that this is log n nodes because the height of this tree will be log n, since it's a balanced binary tree. That isn't, I guess, too important for what balanced binary tree means, but you can see the height here is going to be logarithmic. So when you update a given node, you're going to have to update all of these nodes. How exactly do you do that? Well, what you can do is you can see, okay, is the index that I'm going to update, is it in my left half or is it in my right half? And depending on which kid it is, then you go to that kid and then you tell that kid to update. And now once that kid is updated, you have to look at whatever values that kid stores. So maybe it stores the minimum, maybe it stores the GCD, maybe it stores the sum, whatever it stores. You look at that value, and you also look at the value from your other kid that didn't update, and then you recalculate your own value. So you can do all of that, and you can store the sum or the min or whatever you need to for each node. So after we've updated all of these things, what we can do is we can then answer queries in the same way. So I think it might be helpful. This is a lot of very abstract pictures, and I think they're useful. But I think it also might be good to write a little bit of code to see what that would look like. So I've prepared this this little tester here, and what this does is it just makes a bunch of test cases. So it's just a for loop to 100 for a bunch of test cases, and then I make a new random array just filled with a bunch of random numbers. And now I'm going to ask a bunch of queries in each range. I'm going to take the, I guess I'll take the range sum here, because you can't do that with an RMQ. So I'm going to find the range sum between some L and some R, and then I loop through from L to R, and I find that sum just in this array A here. And then, so I do that half the time, just if it's a random Boolean. The other half the time, I'll pick a random index between 0 and n-1, and pick a random value between 0 and 9, and then I'll set that index here. So I'm going to write a segment tree that will do all of these things, and then I can use this to test whether my segment tree is right or not. And I've already proven that my segment tree is log n. You could submit to a problem that would be a good test as well, or just write data and then run it against it to make sure it's fast. But this will test to make sure the segment tree is right. So let's make the segment tree. So in order to do that, I'm going to make a class for my segment tree. I'm just going to call it segtree because that's easier to type. And a segment tree is going to need to keep track of a couple things. So first, it's going to need to keep track of its leftmost and rightmost indices that it's responsible for. It's also going to need to keep track of its two children. So it's going to need to keep track of its left kid and its right kid. And since this is storing the sum, it's going to need to keep track of the range sum for this entire range. You might want to make this a long if you're doing it for a real problem where numbers get big, but here they shouldn't. So let's make the constructor now. And it's going to take in the leftmost and the rightmost, and also the array that it's representing. So the leftmost of this seg tree is just going to be this leftmost here, rightmost will be this rightmost. And then we have to do a different thing depending on whether we're a leaf node on the very bottom, we're just of size 1, or whether we're going to have two children. And those are the only two cases. So if we're a leaf node, that means the leftmost index we're responsible for will be equal to the rightmost index we're responsible for. So this means we're a leaf. And in this case, we know our sum is just going to be equal to whatever that array element is. In the other case, this means we have two children. And what we want to do is we want to split our range in half and make the first half of that be our left kid, and the second half of that be the right kid. So we can do it like this. This will get our midpoint of the range, and we're going to split it from left to mid, and then we're also going to have mid plus 1 to right. That's how we're going to split the two halves. So L child equals new seg tree from leftmost to mid, and then R child equals new seg tree from mid plus 1 to rightmost. We also have to pass in the array, and that should handle that. So after we have made our two children, we need to recalculate what our sum is. So I'm just going to call this recalc method, and then we'll write this right here. So what does it mean to recalculate our sum? Well, there are two cases. Be void. So the first case is if we're a leaf node again. So if leftmost is equal to rightmost, then we don't really have any children. So we'll just assume that our sum is stored correctly. So in this case, we just can return right away. If we do have two children, then we need to recalculate what our sum is based on our two children. So in this case, we'll say sum equals lchild.sum plus rchild.sum. And now what we have to do is we just call this recalculate method anytime we know one of our two children changes. Okay, so we have this recalculate method, and we can just call that here. We could also call it here if we needed to, but in this case we don't. So now there are two different things where we want the segment tree to do. We want to be able to do some sort of point update. We want to be able to do some sort of range sum. So let's do that. So public int point update, or public void rather. And we also need a public int range sum. So the point update is going to have some index and some int new value. All right. So now again, there are two different cases here. So if leftmost is equal to rightmost, that means we're a leaf. And if we're a leaf, we can just set our sum to be the new value. If we're not a leaf, that means we have two kids, and we need to figure out which of our two kids we need to update. So if index is less than or equal to our left child's rightmost index, that means that we want to update our left child. So that means it's in our left child's leftmost to rightmost range. If it's bigger than our left child's rightmost index, that means it's in our right child's range, so we want to update our right child. So if this is the case, we want to do lchild.update, the same index to this value. Otherwise, we want to update the right child. Now, after we've updated one of our children, we know that they might have changed, which means we have to call this recalculate method. And the reason we have to do that is because as one of these sums might have changed, then our sum might have changed as well. So if like some value in our range was 5 and now it's a 0, then our sum is just decreased by 5. So we need to make sure that we recalculate it because our left child's sums might change as well. All right, cool. So this will handle updating a certain point. Now let's handle taking the sum over a certain range. So our range sum is going to store like a leftmost and a rightmost point of that range. And there are 3 cases like I mentioned. So let's match the order. So the first case is entirely disjoint. So that will happen if the left point of the range is bigger than the rightmost point the segment tree controls, or the right point of the range is smaller than the leftmost point the segment tree controls. So if that's the case, we want to return 0. Because if we just add 0 to something, it won't change it. All right, so that's if it's entirely disjoint. The second case is if the range entirely covers us. So we can check that if L is less than or equal to the leftmost and R is greater than or equal to the rightmost. These are inclusive, by the way, so that's what these mean. And that means if the left point is to the left of our leftmost and right to the right of our rightmost, that means it entirely covers our range. So then we can return the sum, and that's going to be stored here, and we'll keep track of that as we go. So now the third case, this is case 3, which is we don't know. So we have to go to our 2 children and ask them for whatever their sum is. So in that case, we want to return lchild.rangesum from L to R plus rchild.rangesum from L to R. And this will find the sum of those 2 kids and add them together, and this will get the correct answer, hopefully. So let's test this really quick. So what we're going to need is first we're going to need our segment tree and our tester. And the seg tree will go from 0 to n-1, and then we need to pass in the array in the beginning. All right, so this is the range sum query. So int stants is going to be equal to segtree.rangesum from L to R. And now if the stants is not equal to this ants, then we can crash. So this is how you crash in Java. You can throw null. Let's do this point update as well. So segtree.pointUpdate, we need to set this new index to the new value. And this should always handle itself. So now if we run this, passed all tests, I guess we can make n a little bit bigger. And it should take a little bit longer here. I guess that was still pretty quick. There we go. Now it's going to take a little bit, but we just ran a whole bunch of tests and it passes all of them. And like here, we can see if we don't update the segment tree, then it'll get them wrong and it'll crash. So we have to make sure the segment tree updates. That shows it's really affecting the segment tree. So that's how you do point update and range queries. And like I mentioned in the RMQ video, you can write an RMQ. You can also do all of those things with the segment tree if you are okay with having an extra log factor in some places. Okay, so there's one more thing you can do with the segment tree that I'd like to talk about, and that is you can do range updates to it. So this is it's got holes in it from me erasing everywhere, so let's make a new cleaner one. And in order to do these range updates, you have to use this thing called lazy propagation, which is a bit tricky to implement. You got to be careful with it. And I might not implement it live because it would take a little bit of time. I don't want this video to get too long. And I also want to cover some hard segment tree problems at the end for people who have seen this before, still like something interesting. But what you can do is you can do a range update. So maybe we want to update from here all the way to here. So we want to update some range. And in this case, you might want to do some like range add. You can also do like range. What else could you do? You do range multiply, I guess. If you do range add, you can do range add, range sum. You can do range set to, so you could set everything in an entire range to a particular value, and do range sum again. You do set to, and then like GCD, something like that. But yeah, so let's look at just this. So we have some range and we want to modify it somehow. What we can do is we can handle all three of these cases in certain ways. So the first thing we might want to do is, if we're looking at this range here, let's draw it up here. So this is, again, it's case 3. So we have to go down to its 2 children. Now we're looking at this. All right, so now in this left case, this is again case 3 because we can't handle it in either way. All right, so now in this child here, it's again case 3, so we have to go down again. All right, so you can, in this case, we have to go down to both children again. But now we're at this child, and in this child, we can see that now this entire child is covered by the range. So we can say this child had some amount added to it. So maybe it's got like a plus 5 or something. Okay, now we also would be in this child, and now this would also have some plus 5 that it needs to send to its kids. But we're not going to go all the way down to all of its kids because that would be linear time. So we want to avoid doing that. All right, so now again, we're going to be in this point here. This will be plus 5 again because it's some range entirely contained. And we won't go to or when we get to this kid, we'll just exit immediately because it's outside the range. So we don't need to do anything. So now after we've done that, I'm going to erase all of these and draw the plus 5s back in. So we've got a plus 5 here, plus 5 here, and plus 5 here. So now after that, maybe we want to query the min across some range. Maybe we want to query the min along this range. And what we can do is, again, we'll go down here. Let's draw it in blue, because that's what we were doing earlier. So now we'll go down here again. Now we'll go down here. And now we've reached an issue. So the issue is that this plus 5, it's stored as plus 5, but we're going to need to go down to the children. So what we need to do in order to handle this is first we need to update the children by this plus 5 that we said we needed to update them by. So we're not going to update every children. We're just going to update the 2 children segment tree nodes. And then we're going to pretend that we had some range update like this, these 2. And when we do that, we'll get rid of this plus 5 here, but we'll add 2 plus 5s in each half. And then when we go down to this left kid and we try and answer this, it will have been updated by its plus 5, so it'll be accurate now. So if we're trying to get the sum or the minimum or whatever it is, we'll be able to get that quite quickly. Now for this left children, or the left kid here, I guess it's, yeah, it's the left kid of this node. For this left kid, we're going to do a similar thing. So here, we're not going to push the lazy propagate amount down. We have to figure out what the sum would be, and then we return it plus this plus 5. Whether you push it down or not isn't too important in this particular case, because you're hitting the node anyway, but you don't want to push it all the way down through the entire tree, because that might make it linear. So, yeah, what we can do is we can return whatever the sum was plus the plus 5. If we're doing sum, same thing with minimum and stuff like that. So yeah, that's kind of how lazy propagation works. One side note that I'd like to add, or two things that I'd like to add, which are both very important, is that, well, I guess the first one's not important, the second one is very important. The first one's kind of trivial and unnecessary, but worth saying, I think. So in this case, what we were doing is we're doing this lazy propagation where we push stuff down to the root. One thing you might say is, well, we have this plus 5 here, and we pushed this back down to its 2 kids, but that's a relatively complicated thing to do. Why didn't we just get the kids' answers, and then after we had those answers, we could add 5 to them? So that would work if it was min, or if it was max, or sum, or something like that. In that case, we could just take whatever those answers were, and then we could add 5. And if we do that works very well, because we don't actually need to push them down. And that's fine. That works. In this case, the issue is if you have stuff like set2. So if instead of range add, you have range set2, and maybe we want to set all of these things equal to 5. And the issue with that is you run into like timing issues. So it matters when you set stuff equal to 5. So maybe you set this node to 5, and then maybe later on you set all of like this entire node equal to 3. So now the question is, when you're looking at this node, is it a 5 or a 3? And like it matters, because if this 3 got set before the 5 got set, then well, then it's a 5 because it got set to 5 after. But if the 5 got set first and then the 3 got set, this should be a 3. And if you don't push stuff down, if you don't like propagate the fact that you need the set2, if you don't propagate that down, you won't be able to tell the difference between these two cases. So usually it's better to just not try and be clever in that area and just always push down when you need to. The other thing that's kind of important that I'd like to mention is that you have to be able to handle pushing things down in an appropriate way. So that's very ambiguous the way I said it, but here's what I'm getting at. If you have a +5 in this, and now we do another range add, we like range add to this entire range, and now we want this to be like a +3 here. So now we have this +5 and we have the +3. Maybe we do a third range add and we've got like a +7. So now we've done a bunch of these range adds. We have a bunch of these queries that we need to push down. What we have to make sure we do is we have to merge all of these things into a single push down event. So this can't be push down 5 and then push down +3 and then push down +7. And the reason that is we could have a bunch of things we need to add here. Maybe we have a +1 here as well. So we could have like order n different things that we have to add, and then we could push each of them down, and each push down will require a linear number of operations because there are a bunch of things we have to push. So that'll make this n squared, really n squared log n, and we don't want that to happen. Or maybe it's just n squared, maybe there's no log. Regardless, that's way too bad. We need it to be n log n. So that's one thing we have to avoid, and we have to make sure that instead of like storing a bunch of events of things we need to propagate, we need to change this +7 to be equal to, instead of like a +7, +5, +3, we'll just make it like 1 like +15 or whatever the sum is. Then when we push it down, we push one thing down to both of these. So that's important. The other thing to keep in mind is you can mix both range add and range set. And if you want, like maybe you want to query range sum or something, or range minimum, either of those is fine. So if you want like range set, you can store this needs to like be set to equal to 7. And then you can also store like a +5. So you might need to store you want to set it equal to 7, then you want to add 5. And you might even have to store both of those in the same node. And the reason for that is kind of important, because you need to be able to store both of them in the same node, because if you do a +5 and then you do a +7, then the +5, if you try and not store them in the same node, the +5 will get pushed down to both children. And now if you've got this equal to 7 here, so I guess let's draw it on this picture. So if you equal to 7, you push down the +5 to both children. Now you want to push down like a +3. So you put the +3 here, but before you do that, you push this equal to 7 down to both. So this, you've got an equal 7 here and an equal 7 here. But if you try and not store them in the same node, then you're going to put the +5 here, and also to this node, and also to this node, and also to this node, and you'll get equal 7s in both of these. So what you'll see is by doing log n different queries, we're able to hit all of the leaf nodes. So then this devolves into roughly n squared as well, which is again very bad. So we need to be able to store both of these in the same way, and we need to store them in some good manner. And the way I usually like to do it is if you have both a set2 and an add, then you do the set2 first, and then you do the add. So if in that way, If you like set a node set to a different value, you just set the add to 0, you set the set to a new value. And if you add, you don't have to worry about the set2, you just add on top of it, because that's how things would work. And that way you just have to make sure when you push down, first you push the set2 down, then after that you push the add down. So that's lazy propagation, and that's another thing you can do with segment trees. Like I mentioned, it's a little bit more code, so me coding it live might get a little longer than people would like to watch. The last thing that I'd like to talk about is some interesting segment tree problems. In particular, I'd like to talk about Sneetches, because I think this is one of my favorites, and it's like a real classic. So, yeah, it was written by Matt Fontaine originally. So he's the Algorithms Live guy, the one and only. And here's the problem. So you've got a bunch of these Sneetches. It's from a Dr. Seuss book. You may have read it, about Sneetches on the beach. And some of them have stars, and some of them are plain-bellied Sneetches with no stars. And the star-bellied Sneetches are very happy to be star-bellied Sneetches because they are superior in all ways to plain-bellied Sneetches. So they look down upon the plain-bellied Sneetches. And they don't want to play near plain-bellied Sneetches. So what they're going to do is they're going to make friend groups where every consecutive range of star-bellied Sneetches will be like some friend group. And plain-bellied Sneetches, nobody likes them, so they have no friends. So what you want to know is, given some array of ones and zeros, ones are stars, zeros are planes, you want to know what's the biggest group that's a friend group of star-bellied Sneetches. So initially that's pretty easy to calculate if you just have one query. But then, to make things more interesting, Sylvester McMonkey McBean comes around, and he's got this super cool machine where a range of Sneetches can go through his machine, and all of them will change from whether they're star-bellied to whether they're plain-bellied. So maybe in this entire range, initially we had 2 plain-bellied and then a star, and then 2... yeah, so initially we had this. Now we have the opposite. So now we want to know, okay, what's the biggest range of continuous stars? And now we've got this range of 4 here that we didn't used to have before, and that's now exceeded this 3. So now the answer would be 4. And then maybe we change just this node here to be just a circle, or just a plain belly. And now the answer is this 3 again. So if you notice, this is in a segment tree lecture video, so the answer is probably going to have something to do with segment trees. And in fact, it does. And this segment tree is a little bit more complicated than some other ones might be. So since we're doing range updates, we need to have some sort of lazy propagation. And in this case, lazy propagation is going to be whether or not the entire range needs to be flipped. So a node is going to store a couple things. The first is going to be this like lazy prop, which is like, I'm going to call it lazy flip. It's not how you spell flip, but almost. This is going to store whether the entire range needs to be flipped. The second thing it's going to need to store is it's going to need to store the biggest answer within that node. So it's going to need to store the max like range of stars. Max friend group, I guess, would be better. Okay, so it needs to store a couple more things, but let's talk about what we have so far. So if we have this big node here, and it's got 2 children nodes, each of these children nodes stores the max groups of ones within them. And that is somewhat helpful to us. We might have the max groups of ones here, but we also need to know, like, this will handle all of the ranges in our left kid. And this right kid will handle all of the ranges that are entirely within the right kid. But there are still ranges that cross. They go from the left kid to the right kid. And for all of these ranges, there'll be some suffix here and some prefix here. And this kid here, when we're recalculating what the answer is, we need to know the maximum suffix and the maximum prefix. So we need to know the max prefix of ones. And we also need to know the max suffix of ones. All right, cool. So those are both very helpful. Why is that? Well, we can use them to calculate what this max friend group is. There's one more thing that we need to keep track of in order to make sure this is in order to sanity check ourselves, make sure we're okay. Is it possible for us to maintain what this is? Can we keep track of it? And the answer is yes. How do we do that? Well, we can keep track of the max prefix very simply. If the max prefix of the left kid is some sub area of the left kid, so if it's smaller than the left kid's range, then our answer is just going to be the left kid's maxed prefix. The other case is it's possible the left kid is all ones, and then there's some area in the right kid as well. And if that's the case, it's the size of the left kid plus the right kid's max prefix. And then suffix is the same, just flipped. All right, so now we can maintain both of these prefixes and suffixes, and we can also kind of maintain this max friend group. There's one issue though, and that issue is if this has the lazy flip inside of it, or maybe let's say one of the kids has the lazy flip, because if this has the flip, we can just push it down to its two kids. But now let's assume that this right kid here needs to be flipped. And now we have an issue, because the right kid needs to be flipped, and it's storing its maximum range within itself of ones. But all of those ones, when they get flipped, will all be zeros. So now we're keeping track of the max range of zeros, but we don't know what the max range of ones actually is. So in order to do that, what we have to do is we have to also keep track of what the maximum range of ones is. So this is like the max range of zeros. Or max range of ones. We also need the max range of zeros. And in order to maintain what this max range of zeros is, we need to store the max prefix of zeros as well, and also the max suffix of zeros. So now we need to store quite a few things. We need to store whether or not this needs to be flipped. We need to store the max range of ones, and we can calculate that by doing a couple things. We need to look in our right kid and see what's the biggest amount of ones in that, what's the biggest number of ones in the left kid, and also we need to look at all the ones that cross the two kids. And then in addition to that, we need to calculate the maximum number of zeros in our entire range, and we can do that by looking at our left kid and our right kid. And we have to take into account, as we look at these two kids, whether these two kids are flipped. And if they're flipped, instead of looking at their zero values, we'll look at their one values and vice versa. So by doing that, we can handle all of these things, and we can keep track of, for the root node, what its max range of zeros will be. And that's exactly how we solve the problem. So that's Sneetches. I think that's a very interesting problem. It uses both lazy propagation and well, I guess it uses lazy propagation. It uses segment trees, and it uses this interesting handling ranges separately from both the prefix and the suffix. So like I mentioned, this was a much simpler video on segment trees. It just covered kind of the basics and lazy propagation and stuff like that, as well as a kind of interesting problem. But in the next two videos, I'm going to talk about segment tree beats, which can cover some really cool range min width and range max width operations, and also persistent segment trees, which you can use for a lot more slightly more difficult problems. They're a lot more powerful as well. So thank you for watching, and hope you're excited for the next two videos.